But Sarvesh, people do post questions on the chat, Zoom chat channel. So if you can keep it open, if I see some, I will also interrupt
Okay.
and let you know.
Yeah, I think you should just interrupt me because I think I can just see my screen right now. I can't see
Okay.
the chat window. So I don't want to
Okay.
fiddle with that now, but please feel free to interrupt me if there are some questions and I can chime in and answer them.
Okay. So this is the last talk on the exascale systems, Aurora, much closer to my heart for obvious reasons since I work here. And so, Sarvesh, go ahead.
Okay. Hello, folks. Must have been a long day. Hopefully, I will try to keep the details to a very minimal and try to give you a nice overview that covers like history and then architectures and all of HPC. So my name is Sarvesh. I'm a computer scientist, work at the ALCF facility here. So without much ado, get started. So, okay, so a brief background on ALCF. It was established in 2006. We have a sister lab, which is Oak Ridge. So we both come under the leadership computing facilities where we try to bring up new architectures and new computers that try to be at the forefront. There are other facilities as well. No doubt you've heard some talks about NERSC and other folks since the morning. A bit of a broader landscape here is that we have other centers as well, like TAC, PSC, and so on, just in the US. And then if you go throughout the world, there are other facilities in Europe and Japan and China and stuff. The key thing is their LCF facility, there are two of them. That's Oak Ridge and ALCF here. For allocations for the supercomputer, we go through the Insight program, which is basically scientists apply for compute resources using core hours, and we try to budget that into a program where we try to allocate hours based on the merit of the program. Okay, so I didn't want to get really started directly into Aurora. I just wanted to give a brief background on the several supercomputers that we have had at this facility so far. So what I will try to do here is that I will try to give a brief overview on HPC architectures on the next slide. And then I try to highlight what has changed since we had Intrepid and we have Theta right now, and what's going to be coming up in Aurora as well. We said 2021, but it's going to take like a year or two to get the whole machine on the floor. So again, if you have some specific questions on the architecture along the way, please feel free to stop me and ask the questions. I know it's been a long day, but still, like if you have some of the questions, I'm really happy to answer them. Okay, so before we go into the machines themselves, just wanted to highlight what we have, the different components or the different parts of a supercomputer. So in this slide deck, we will be basically going over the processor architecture because that's the most interesting, because that directly relates to the performance. But there are other parts of supercomputer as well that are quite essential for its full functionality and stability as well, right? Like, you'll quite closely understand, like seeing all the slides that you have seen since the morning, that like having more than one system connected together brings in a lot of challenges with IO, with control system and everything. So therefore, there's a lot of complications involved in the backend of supercomputer, even though I'm just going to stress on the processor architecture in this presentation. I will touch base on memory slightly wherever that's important and highlight just the network as an overview. But essentially, these three would overwhelmingly form the fundamentals of what we would call an HPC cluster today. So one key word that has been driving HPC or its improvement is performance over power. So how much you can get per watt and how much you can budget in a particular facility. So that usually forms a limitation, and every generation of supercomputer gets more and more efficient in several means to get more performance out of a system through several different approaches. Okay. So diving right into what the processor architecture generally can be classified into. Traditionally, back in the 90s, Dennard scaling was pretty much very easily applicable, and you would see processors just coming out every year or every 6 months, but to just basically gain more clock speed. And people thought, at some point that would be the way we would get more performance. But quite soon we reached a point where increasing clock speed would basically be an enormous weightage on the power required to drive the processor. Therefore, that became a very limiting factor. And quite soon, parallelism took over as the way to get increased and large number of computations being done using these several processing cores. And there are several types of parallelism. I would not go into each level in detail, but HPCs typically derive parallelism from having multiple compute cores, right? It could be via compute cores in the processor itself. It could be multiple nodes consisted of multiple cores, or it could be GPUs, which again have further lightweight cores. So HPCs have generally revolved around that for the past more than a decade at this point. But there are certain other factors as well that's been, kind of helping improve performance. Some key things are instructional pipelining, which basically allows you to schedule more than one instruction at the same time, depending on the available backend. And there are large vector widths as well. That was, giving ability to compute, using one instruction, but using a very data parallel manner to perform multiple data operands in a single cycle or a single compute instruction, essentially. Memory has been going the other way around since processor speeds have been improving in a very drastic manner, but memory has still not been able to keep up with the demand for the computation speed. One way architectures have been smart to get around that is to have hierarchies in the memory system by using several layers of caches. The other way is to use some kind of an intelligent mechanism to prefetch and to predict what kind of memory data operations the instructions might need, and then pull it into the lowest cache available next to the processing core. So this has been dominant for over a decade, I would say, but recently things like ASIC processor, essentially processors designed for a specific computation, have taken over. One of the things is tensor cores, which are heavily used in computational neural networks, which forms the basis for artificial intelligence-based computations. They are basically GEM, just basically designed to do matrix-matrix multiplication at different precision levels. And people have tried to use that to do several other computations. And it tends to be that the future arena of HPC might look like specialized processors put together in a large cluster. But again, only time will tell what particular architecture will prevail in the decade. So we have lived through the data parallel era where we have just fundamentally scaled with more cores or specific process that would have helped us gather more performance, but that might not be what it stands as we move towards the future. So before I go into the several generations of supercomputer, are there any questions on just the architectures alone? I think I see something in the chat window.
No, that was an earlier question for
okay.
Brian. Yeah, so you're fine.
Okay, now I need to try to close this window. Oh, shit. Okay, not able to close the chat window. Okay, let me just ignore that and go. Sorry about that. Okay, so back in 2008, we had the Intrepid system. So key things, I'm not going to tell you the exact number and stuff. You can basically read it on the slide. But essentially, what you need to understand is the node to core combination, right? You have one node, and basically you have around 4 cores on the node, and that basically was the first kind of ratio that we started out with at the ALCF facility here at Argonne. But that's changed slightly as we move to different generations. I will try to highlight what brought about the change and to show how that translated to the performance improvement that we got between the different clusters. So when this came out, it was a top 6 in the supercomputer, in the top 500 list. Yeah, I see a question. Intrepid seems to have a lot more nodes than modern systems. That's true, because the PPC cores were extremely lightweight and very less and very simple in complexity, right? As we have moved over generations, we have reached a point where the cores themselves are becoming was becoming more fatter, I would say. And then we had the GPUs that kicked in, where they slightly went back in design, where again, the cores themselves were threads, which become very small and very simple in complexity in nature. But then you get to try to put more of those GPUs in a single system. And that is what the trend has been in the recent years, I would say. Yes, there are a lot less nodes right now, but per node performance is a lot more in the recent systems. And that is why we have a lot less nodes. Again, as I said, power is the budget. If you have infinite power, you could probably build up as much of a cluster as you want, but at some point you're going to reach the point at which you can't translate the given power available to the facility itself is going to be possible to limiting your size of a system that you can have. Okay. So just just a brief overview on the architecture. Like you don't need to worry about too many of those details in the diagram. Key things that I would recommend just to have a glance at is this manufacturing nanometer scale, which basically means that how many gates you can actually put in a given silicon size. This is a 90 nanometer fabrication scale that was done at the die size of just slightly over 1.3 centimeters. There were 4 CPU cores per node, essentially. And then you will also notice that there are 5 network interfaces on the chip. This basically forms the HPC interconnect that the system would use, which I will try to come the slide after next. This used a very, very old memory system. Right now, it was DDR2 in the past. So that is what was state of the art at that point. Nothing very fancy with the memory. It was just a standard off-the-shelf memory. And Blue Gene was pioneering this, trying to use this PPC core, which was a code that IBM very well understood, and to try to use that to build up such a larger system. The cutoff thing was to try to put together a system of such large scale and to devise a mechanism that would be utilizing it in a very effective manner. So going a bit more into the details on the architecture itself, right? Again, some of these are still true to this day, different systems still use some parts of architecture. So that's not something drastically changed. For example, you have in-order execution, which basically means that instructions have to be executed in the same order that it has received. Newer generation processors can do out-of-order execution, which basically allows it to schedule more than one instruction from the pipeline at the same time, depending on what is available as the resource. But to simplify the architecture here and to allow you to have more parallelism, silicon was basically just going to do in-order execution that saves a lot of space from this extra complexity. So what we call as execution pipelines essentially refer to the parts of the processor that is responsible to do the actual computation itself, right? Here you have the simple integer and the floating point computations, which are responsible to do the actual flops calculation. And then you have the memory part of it, which is the load store units that basically corresponds or translates to pulling in memory from the different addresses, I would say. Again, there is a brief highlight on how the instruction pipeline executes in 7 stages. You really don't need to fully understand what it is. Essentially, it's the same as you would expect from any processor. You have the part where you have to decode or fetch an instruction, issue it, and then do the address presentation to pull in the data, and then issue it to a particular pipeline. And once the computation is done, write it back. One innovation here was that you could issue 2 instructions per cycle. Again, this depends on what are the execution pipeline that is available for at the time. So, but that was possible to schedule 2 instructions to be executed in the processing core at any given cycle, right? Instructions per cycle is something that you would commonly refer to till this day to understand what the scheduler or how well the scheduler of a processor can be designed for. modern Intel processors can do 4 instructions per cycle, right? Again, if you're going to do large vector width computations, this instruction per cycle will go down because the complexity of issuing those instructions are a lot larger. Just to compare the new and the old, like not much has changed, but just to give you an idea behind what kind of transition has happened through the generations, I would say. So as I mentioned, like processing speeds have been like, quite large, and memory has been trying to keep up. Memory, I mean, memory bandwidth and memory latency, it's not been able to keep up with the processing speeds that these modern processors can do. This has been a challenge since the dawn of computers, I would say. But maybe in the early generations where the vacuum tubes, they would have been like, memory could have been slightly faster, but more on the modern side of things, it's always been that memory has been several steps behind what a compute can do in a sense. So one way that classically processors would try to address that is to just divide the memory subsystem into hierarchies. So we essentially refer to memories that are closer to the processor as caches, or even in the same silicon as caches. These are SRAM cells, which essentially are like much faster and have more ways to access. Whereas off-chip memory, like the DDRs, you have to go away from the silicon and to fetch it via an external link of some sort. Like, you have the double data rate bandwidth, right? Like you have serial links that connect and parallel links that connect the silicon via system board to the actual memory itself. That's going to be a lot more slower. Whereas the caches, which is a part of the silicon, they could essentially wire them together and couple them together much more easily, and thereby allowing you to access them much faster. So there is some numbers here which tell you that as you go from level 1 to level 3, it's going to start increasing, and you will see the latency goes up. But again, the size of the memory that each cache can hold also increases, right? So further you go down the hierarchy, the larger the memory you get access to, but the penalty you pay is that you have more cycles to access them. So there are several mechanisms that a modern processor does to try to utilize the cache as effectively as possible. One is that it can try to look at the instructions that are being issued and try to see if some of them could be pulled in quicker. So things like that were tried and tested, and this has been like a standard thing that any processor would do even till this day. So one interesting thing you need to understand is that, like, with such a number of nodes, a large number of nodes, the network becomes a very challenging part of the supercomputer, right? Like you need to be able to schedule computations on all of these nodes and to do that in a very effective way. I won't go details on MPI, maybe that's a session later on in ATPESC where the software people go through that, but what you need to understand here is that when you look at parallel code, like you're trying to essentially divide the work you want to do across these large number of nodes. And in doing that, you would encounter some very standard kind of computations, like a collective operation essentially lets you gather all the work from all these different divisions that you do on your computations, and then put it all back together in a single point. And then you have like some kind of a barrier where you don't want all your parallel threads or processes to progress further than that point. So BlueGeneP did something interesting where they divided the network into 3 different parts, right? Like, they dedicated a 3D torus network, which essentially means each node is connected to 3 of its neighbors, and that allowed it to do the transmissions between them for MPI send and receive through that particular network. But then they dedicated a collective network and a low latency barrier network that did this larger complicated MPI computations or MPI operations in a dedicated network to reduce whatever that effect might have on the overall computational time of performance. Because if these operations take too long, then it would affect your overall runtime of your code itself. So just that part alone is what's more important that you can grasp from this particular slide. So moving on to the next system, we have the successor of BlueGeneP, the BlueGeneQ. We recently retired Mira. It's been in LCF for quite some time. When it was released, it was the top 3 in the top 500 list. So here you would notice that the number of nodes have been somewhat in the same order, but the number of cores have drastically, jumped to a larger number. The simple reason being is that between those years between BlueGene P and Q, the silicon manufacturing technologies have greatly improved. From 90 nanometer, now you have the 45 nanometer fabrication scale, which allows you already to be able to put in a lot more transistor. But apart from that, the yields were better with the 45 nanometers, so you could go to a larger silicon and thereby getting in the order of 1.5 billion transistors or gates into this particular die. So this allowed, to drop in close to 18 cores. Again, these were lightweight cores. They were not super complex cores that you would find in modern processor, but they allowed you to the required computations that you're expecting it of. One thing here though, not 18 cores were available for computation, 16 were dedicated for computation. One was used for just to maintaining the system OS functions, and one as a redundant core. You would also notice that the instruction caches compared to a modern processor is very, very small. Again, this is the same deal, right? You cannot put more caches onto the silicon without paying a trade-off in the amount of power that it consumes, right? So we trade that off to get what we can for the silicon for a given power budget or power envelope, I would say. Technology-wise, we have EDRAM that was introduced for the L2 cache, and then you have DDR3 memory. Again, DDR2 to DDR3 is a much faster memory fabric, everybody understands that. So I'm not going to give numbers here. So key things here is that since you have a lot more cores, you have a complicated crossbar switch, right? So this is something that's still trending till this day. In any architecture you would see, the more the number of cores, the complexity of connecting them also increases. So here we have a crossbar switch mechanism, which allows you to do the communication between the caches and the compute units themselves. So memory hierarchy wise, here we see a bit more complex handling of things. So like I said, prefetching was introduced in this arena where you can look at the instructions being executed and try to understand if certain memory data operations which are not dependent on executing instruction could be prefetched into a particular cache. And this crossbar that I mentioned before was doing quite a complicated on-chip networking system, which essentially allows you to do a bit more complex look-ahead operations for the memory hierarchy and to handle it better. So they had dedicated on-chip memory controllers, a bit of details on the latency and the bandwidth on the top right box here. So key thing is that, since the processors have gotten faster, memory has to again ramp up. And that's essentially what this was trying to do, try to make the memory subsystem keep up with the increased performance that you could get out of it. So the core, overall, it looked very similar. There was nothing drastically new, but there were certain things the instruction issues where try to give multiple threads, I would say, but these threads are basically means that you have the particular registers that are responsible for doing a particular operation or the issue instruction, but the actual cores themselves are just whatever physically present. But then the scheduler will try to switch between these virtual threads in hardware such that it can compute if one particular thread is held back on a memory issue or a memory dependency operation, thereby trying to keep the hardware busy as much as possible. Multi-threading in hardware is something that's till date been used still, and you will see a 4-way SMT is what this particular code does, but Intel processors typically do hyper-threading. You have AMD processors, they do some kind of hyper-threading as well. So hyper-threading has been one way that processor architectures have tried to get around trying to keep the compute pipeline as busy as possible by trying to switch between different context or different threads in hardware, essentially. Not to be confused with the software threads. That is a totally different thing. These are actually in hardware, and they're a lot faster in executing them. In fact, you actually see them as virtual cores when you run it on any model system. So again, now the challenge again is that that network that we saw in the BlueGenP was a lot less complex compared to what we have here, right? Like we call this the 5D torus, and this essentially you don't got rid of the separate collective or the barrier networks, and then the networks themselves got a lot more complicated, and a lot of software backend handle the collective operations through specific hardware engines in the network processor itself, I would say. So thereby, they could reduce the overall complexity system, because if you have 5 different network on-chip, network dies on chip, that essentially is a lot more complex hardware. Right now, you could reduce that into 3, and then that allows you to slightly get a better overall scaling of the system itself. Some details on exactly how the architecture looks it's in the corporations over there. So I wouldn't go through much details on it, but just to understand that the complexity here has gone up, but you trade off, you don't need the separate networks for the collectives of the barrier that you saw in the BlueGenP. So theta is, okay. So I have a question here. After a supercomputer is retired, what happens to the components? It depends on the facility completely. So depending on the life of the system and depending on how the the procurement process is, you might need to have a separate bid to take the system away, or you have separate scrapping yards, or they donate it to different labs. It all depends on specific labs, procurement rules and guidelines, and something that I'm not very privy of, I think, at this point. But each facility has their own rules and regulations around it. Okay, so going back to theta. So theta is still in existence or in our ALCF facility right now. It's a system that people could apply for an Insight program to get allocation hours on it. So that's quite a big jump, right? Like till now we were using the IBM PPC based BlueGenP and Q systems, and now this is the Intel's Knights series of processors. They were a process generation before what is there in theta. So it was an evolutionary approach where you only see one particular snapshot of it, but there has been processors before, and there was supposed to be one after, but that never progressed because it didn't work out to the best of everybody's interest, I would say. Key things let's go into the architecture. That's more interesting than what we have in the overview. So here now we see a sudden jump, right? Like we have gone down from 45 to 14 nanometer for the manufacturing process for the silicon itself. That coherently gives us more transistors on the same silicon fabric. Again, as years have moved on, yields for getting a larger die has improved. Now we have a larger die size, 6.8 square centimeter die size. So that's quite a big die. So what do you get out of it? You get 64 cores now. There are some variants that could go more than that, but 64 is a nice number. Let's assume that. The challenge, as I said before, is that having more number of cores is going to keep the connectivity between them a lot more challenging and a lot more complex. So here, what Intel did with this is to come up with a 2D mesh interconnect system, where you will see this nice grid pattern and all the different tiles are connected together in this mesh system. And this mesh is the way the tiles access the different memory parts of the system as well, right? So as I mentioned again previously, memory has not been able to keep up with the compute speeds, right? So here we have one new innovation where they try to package an MC DRAM, which is similar to DRAM, but it's not the same, into the same base die, right? So when I mention a base die, I don't mean the same silicon where the processing cores are, but adjacent to it. So one example is that if you look at, like, for example, other GPU vendors at this point, they have HBM memory, right? So they have it in the same die, but they are next to the silicon itself, like, they're not, and they're connected through some kind of a high-speed interconnect between the two. Similar to that is what I would think of or imagine here for the MCDRAM system. So one other key thing that I would say, this particular KNL or the Knights series of processors, that is that they try to exploit large vector width computations, right? Like typically, this is a 512-bit instructions could be issued with the Knights landing this particular processor, and this allowed you to do 16 single precision computations in one issue operation. What that means is that the complexities with the instruction issue and those parts of the processor could be greatly reduced, whereas you get, like, maximum amount of performance or computations out of the given silicon space. But this translated to having a more complex compilers and more complex software libraries, I would say, that can generate these particular instructions and ability to handle them in the programming layer or the programming model that you're going to try to challenge it in. If you were not able to write massive parallel code or generate massive parallel code, you wouldn't be able to taking advantage of these large vector width operations, right? So that was the key challenge here. Also, by introducing this new memory domain where you have, like, an on die or on silicon, like, MCDRAM, you tend to have another new hierarchy introduced to the memory subsystem. You have the caches and you have the MCDRAM and the DDR4 that sits off chip as well. A bit more detail on a detailed diagram on how the style hierarchy looks, right? Like you have the different compute tiles, and then you have the CHA, the coherency interconnect fabric that connects these dies together. And then you have different tiles that specify, like, EDC is the memory controller for the MCDRAM, and then the IO operations a different tile altogether. And as I mentioned before, all these are connected via this complex mesh interconnect, and they all go through an XY routing. So if tile at the furthest end has to go to the top end, it has to go through this fabric using several hops. Like, like imagining a very large computer shrunk into a very small silicon die. They were all cache coherent, and they used a specific hardware protocol for that. And for the memory itself, there's a slide after this, which I'll go to memory, but just going back to the tiles, as I mentioned before, they have large vector units. That was the highlight for this. And that essentially would allow you to issue like a 512-bit vector instruction and operation. Going into the caches itself, you have the L2, which is like, on the die itself, like, that's around 30 to 36 megabytes, depending on the configuration. And then these are all coherent across the entire tile. So the more interesting things are more in this slide. So the process fundamental itself is pulled from the Silvermont architecture. And this is basically the Atom processor. So basically the instruction decode and those parts of it. But then Intel introduced and made a very complex formulation for the backend computations, right? Like the highlighted in orange in this slide here. That was directly responsible for doing all of the computations in the system. So we have the same hardware threads, as I mentioned, like, as you saw in BlueGene P, so which allows you to use hardware registers to save the state of a particular execution context, and then switch around depending on which execution context is ready to issue operations to a particular computation backend or a particular functional unit in the backend. One key thing is there you will see something called out-of-order execution, right? So this is a very important, like, I would say a consideration, a very important change in the hardware architecture. This actually distinguishes from a very lightweight GPU to a more complex CPU, which becomes important in later slides. Out-of-order execution essentially puts in a complex instruction fetch and decode unit. Essentially, it goes into the history or the hierarchy of the instructions being scheduled and tries to pull out instructions that are not dependent on each other. Thereby, you could issue two instructions which have not occurred in the same order, which have not come to the same order to the processor. This greatly introduces and improves the throughput of the entire processor. You might still have some instructions that have to be put on hold, but most of the time you will notice that if you have very parallel processes being scheduled onto a single core or a single processor, you could use these out of order execution to a lot more advantage. And if there are some of them which are dependent on specific memory operations and they're going to take a lot longer to pull in the data to the relevant cache, you could essentially get a lot more benefit out of order execution. It's essentially hiding the latency of the memory subsystem and trying to give the processor a chance to execute something else, and thereby keeping its functional unit as busy as possible. So again, I wouldn't go details into what MCDRAM is. Just for a very brief highlight of it is to just say that it's a larger or higher bandwidth memory. It's in package, right? Like it's next to the silicon die, so thereby you could connect it much closer and couple it together, allowing it to get more bandwidth out of it. Then you have the hop chip DDR as well. Again, you can see the 485 versus 90, which is just like, you have roughly 4 times more bandwidth that you could get to MCD RAM via DDR. So more memory domains you have, the more you will start seeing NUMA effects, which essentially means reaching a particular memory space from a given core. You might have different paths that you might take. And that is what we essentially call as NUMA, or non-uniform memory address space, where modern processors all suffer from it, but they have different mechanisms to handle it. One way, how KNH or Knights was like trying to address this is to try to introduce different memory modes, I would say. So one was to have a cached mode where essentially data would flow through DDR, and then through the MCD RAM, then you have the flat where you can schedule memory onto both the DDR and the MCD RAM, and then you have the hybrid approach where you will try to combine portions of the memory as a cache and portion of the memory as a separate part of it. So there were several memory libraries that were introduced in the software layer that could take advantage of these things.
So Ray, just wanted to let you know that you have 7 minutes. So
yeah, sure.
Maybe you want to switch to the Aurora side.
Yeah. So again, the network got a lot more complicated. That's all you need to take from this slide. Again, in the interest of time, I wouldn't go into too much details into it, but again, Aries interconnect is it's an interconnect that's been around for long. So if you want more information, I can definitely think Google is a good way to gather that. So going into the crux of today's presentation, again, the system Aurora is being right now being developed, installed. I can call it in different ways. So we cannot share a lot of details about it, but I've tried to gather the information that would be very interesting for folks to understand today. I will be only focusing on the part of the system where you would get the most amount of compute out of it, that is a GPU, but I would try to give you a bit overview of what the CPU is as well. So this, as an overview, you have the compute planes, right? That basically consists of 2 Xeon processors and 6 GPUs, and they have an all-to-all connectivity between all of them. So there's estimated to be 10 petabytes of total memory across both the CPUs and GPUs across the whole system. There is an open source DEOS subsystem for the storage part of it, and a Slingshot fabric and a Shasta platform for the interconnect system between all these different cabinets. Okay, so the 2 parts of the compute plane, I would say, the processor, which is going to be based on a Sapphire Rapids Xeon CPU. So again, 3 things here to take away is that now we see a memory jump to DDR5, which is going to double the memory bandwidth capacity that you can reach. You also have PCIe Gen 5 that the processor will support, which again allows you to do a lot more faster IO operations. And finally, Intel is also trying to introduce high bandwidth memory as part of the Sapphire Rapids, the same on-package die kind of memory, similar to how you saw on the Theta system where we had MCD RAMs, but now you have a much faster and a much better understood memory bandwidth like HBM. Going to the right slide is where I've tried to grasp an image of the Ponte Vecchio graphics representation of the slide, because you can see that it's a large die, right? You have so many different components that have been put together, because it's not a very simple CPU, as to call it. You have several different tiles that does different computations and different operations, and the packaging itself is quite complex, and all this has brought about, like, like so far the biggest silicon, or the like that you can see for such a computational operations. Again, not going to go into too much details on this, but they have put on links, and I'll try to share these slides after the presentation. And there's a keynote presentation that Intel gave on ISC, which goes through the details, and that way they get to say what can be said and what cannot be said, and we cannot reveal too much of information on this. But what I can talk about is the things that have been like public platform. Like Intel GPUs are not something that's just come out in a year or two. There's been several generations of it. In fact, Skylake nodes used Gen 9 version, and as years more on, there's been versions that have been iterated on top of that, and that's been slowly made more complex and fine-tuned and improved in performance as it moves from like more of an integrated GPU designed primarily for graphical works to more of a discrete GPU that primarily focuses on computations, I would say. So Intel has this dynamic kind of configurable architecture in their mind, where they try to fine tune this architecture for different purposes. Slide on the right shows the different generations, the low power to the high performance computing variant of it. So the next few slides, I will just go into the high level architecture of the XeGPU, right? Like, again, do understand that each particular architecture configuration might vary. I'm just trying to show you a general overview of how the Xe architecture looks like based on what is available out there at this moment, right? So this might not be the exact architecture, and there might be some changes, but I wanted to give you a more of a general overview of what would be the fundamental backbone that directly contributes the most amount of computations or performance of the Aurora system itself. So you will notice immediately is that this is a top level view. This basically is the largest view that you can get. I'm going to break it down into each level as I move through the slides. In this slide, you can see that you have different slices and a particular command front end, which essentially forms the unit to issue and decode and like schedule different computations onto these different slices. And each slice again is divided into a sub slice, and then so and so on into the EU array itself. Again, as I said, I will break down this each into a different slide to show you and explain to you what difference goes on in that. For this, the memory fabric, it comes at the at the top level. So if you were to look at any GPU architecture today, you will find that they tend to sacrifice more complex computational units in order to trade many of them in a single silicon die. So this is basically like, a many core architecture, I would say, closer to that. But GPUs appeared and evolved to the direction in different form compared to what you saw in the Knights series of processors. Going into a bit more delve into just the compute subslice itself. So you will notice that there are more units in a particular slice, right? Like you just don't only have the units that respond for the computations. You have some other units that do like, the geometry rasterization operations. These units are more important when you have the graphical front end or the graphical component of the particular processor. As I said, this is a configurable architecture, and I'm talking about more on things that are public information. So, and depending on system that's being used, these could be reconfigured to do different things. So moving on to the four or the fundamental part of it.
How much more time do you need?
Just 1 more minute. I think this is the last slide.
Okay. Okay.
Yeah. Just so basically you have 16 EUs grouped into a particular subslice, and you have different, each of these EU are the ones that are responsible for doing the particular computations or the particular operations that are being done. So they also have like the memory instructions being into it, and then they all are connected together using a high speed, on the interconnect of some sort, and then they all operate as one big unit together. And then a thread dispatcher essentially is where you try to schedule particular instructions or particular operations onto all these EUs to do some specific operations. So a bit more detailed look at the EU. Again, you will see a similarity, right? Like you will see a backend pipeline which does a specific like floating point or integer operations or a specific memory control operations or any of the sort. This is the same as being like, for several computer generations at this point, right? So, but certain fine tuning of architectures to those specific computations is how different manufacturers differentiate between different generations of the processor, right? Here, this has been fine-tuned to do specific kind of computations, a specific kind of operations in a particular fashion, I would say. So final slide here. So Intel GPUs, like, there's nothing like you folks, if you want to try it out, there are like, several ways to get access to it. Like most modern laptops, like, from Gen 9 onwards, have the facility to and the ability to run these computations. There are lots of material online. Most of the material Intel develops has been in the open source domain. So therefore, like, many folks can get together and try to get on using it. There's also this DevCloud facility that allows you to request an account and try to get access to specialized hardware should you be more interested on it. And that's my last slide. And sorry for taking a minute longer. If you have any questions, I'll be around. And if you want, you can post me in the Slack channel.